Okay, friends, so we're going to dive back into distributions here, but I figured before we do that right away, tying into that topic, I want to revisit the definition of probability again, too, just in case, since we're getting back into probability via the first project and also this new topic of distributions, just reminding ourselves what probabilities actually mean. So we're going to use our single die again, because I've always liked using dice in this class. Yesterday we talked about rolling a single die and having a chance of getting, say, a 2. What's the chance of getting a 2? And I think we pretty much said 1 in 6. If I was in class with you, I love asking, what does it mean to have a 1 in 6 chance? And I love kind of pushing buttons on people, like, what does it mean to have a 1 in 6 chance? When I'm in class, I get usually these kinds of answers. There's 6 sides, and one of them is a 2. I can't find it right now. Oh, there it is. And one of them is a 2. And I say that's true. And I said, what else is there? There's something else besides just having 6 sides and one of them being a 2. And eventually I tease the answer out of folks. But what some people say is, well, since there's 6 sides, if I roll the die 6 times, I'm going to end up with one of each of the sides. And then I go like this. And they go, why are you... I'm like, give me more. And they're like, there is no more. So I want to explore that kind of statement. If I roll a die 6 times, I'm going to get each of the sides. I want to explore that statement next. And we're going to come back and back and back to that statement because I think it hammers home the definition of probability. So what I'd like to do right now is actually do the experiment. I'm going to grab 6 dice and roll them and see what happens. Let's take a look. Okay, my friends, so we're going to take these 6 dice and we're going to roll them all simultaneously and we're going to see what happens. Now this would be the same thing as rolling 1 die 6 times. I'm just doing it this way. It's easier to keep track of what would happen without rolling 1 die over and over again. So remember, the claim by a lot of students is a 1 in 6 chance when you roll a die means that every 6 times you roll the die, you get one of each of the numbers. Let's take a look. Okay, so there's my first roll of 6 dice. As you can see, we've got some repeats. We've got 2 1s and we've got 2 6s. Also a 2 and a 5. We're missing what? We're missing 3, we're missing 4. Okay, let's roll it again. All right, what do we got this time? We got 2 3s, 3 6s, and a 2. Interesting. Let's roll it again. Okay, what do we got this time? We got a couple 4s. We got everything except 5 and 1. Huh, interesting. The theory seems to be falling on its face. Okay, what do we got this time? Let's put them all together here. We got a 2, a 5, a 6, a 3, a couple 2s, a couple 3s, 5 and a 6, missing a 1 and a 4. So what the heck's going on here? 1, 3, 5, a bunch of 5s, a 3, a 4, no 6, no 2. So what's going on? I mean, I'm not seeing one of each. 1, 2, 3, 3. Oh, we almost got it that time. Look at that. We almost got it. We got a 3 and a 3. We didn't get a 4. But what the heck's going on? Like, 3 6s. What's going on? I don't understand. Where's the 1 in 6? Okay, friends. So what I did here was I kept track of what happened in those last few rolls because I wanted to see if I could tease out the 1 in 6 or the 17% probability. Now, as you can see in the results, it looks like I got close to 17% with a roll of 2 pips, which means I saw 2 dots on the dice about 17% of the time. But then, 6, I saw quote unquote too many 6s and quote unquote too few 1s. Now, if these dice are, as I say, fair, shouldn't those percentages be closer to 17%? And the answer is yes. And the quick, easy answer as to why these percentages aren't is because, well, honestly, I just haven't rolled enough of them. This is the big takeaway from probability. In the world, when you're trying to observe the incidence or occurrence rate of something, you have to watch the experiments enough times to establish the rate. And in this crazy world we live in now, where we're so used to things happening instantaneously at the drop of a hat, showing up in our phones,
at the speed of light, we forget that sometimes, that a lot of times with research, it takes cautious and conscientious and constant observation. So I propose we do that now. I set up a spreadsheet in Excel to do exactly what I did previously, which was rolling dice over and over again. But I'm going to have Excel roll a die for me. Now, I was rolling dice 6 at a time to prove a point. What I'd like to do now is just simply roll 1 die at a time and have Excel keep track. So right now, if you take a look at this probability distribution, I've got these 2 extraneous columns in the middle, E and F. That is simply a current and cumulative frequency column. That's going to be keeping track of the experiment as we go. For example, right now, Excel rolled a 4 using the rand between command, 1,6. So every time I refresh this spreadsheet, you're going to see a new random die roll, quote unquote, between 1 and 6. Here, I'll do one right now. There, I just rolled a 5. So I've now rolled a 4 and I've rolled a 5. Okay, now, if you look at the probability column, you'll notice that it looks very, very strange. It's like, wait a minute, how can they both be 100%? They should be 50% each because I've rolled 2 total rolls and I've gotten 1 each of 4 and 5. If you look at the formulas that are in those cells, they should say 50%. I don't know why they don't. It's a mathematical mistake that Excel has built into it. I've been trying to track down the solution for over 15 years now. The good news is, if we keep rolling more and more and more, the error goes away. So I propose we just keep rolling. I'm actually going to roll 4 more times just to kind of reiterate what we saw in the videos we just looked at. Now look at right now. I just rolled 6 total dice, and I did not get 1 of each. So my question, I guess, to everybody is, what does the 1 and 6 mean? Well, I propose that we simply hold down the F9 button and let these dice go out and do their things. Do what dice do, so to speak. And now, hopefully, you're beginning to see the 1 and 6. Sure, they're not perfect. Sure, they're not perfect. But all of a sudden, after rolling, let's see if I can stop right at 600. There we go. After 600 rolls, all of a sudden, the probabilities are much closer to 1 and 6 than they were with only 6 rolls. So earlier, when I said the students told me that a 1 in 6 chance means if you roll a die 6 times, you're going to get each of the numbers. And I said, give me more, give me more. What I meant was, you need a couple more words to quantify that. For example, if you roll a die 6 times, you will get 1 of each of the sides on average or over time. It doesn't mean that every single 6 times you roll the dice, you can expect 1 of each of the sides. That's not what it means at all. As a matter of fact, we didn't see that at all in any of the examples we looked at just now. I'm not saying it can't happen. I'm just saying it doesn't seem to happen very often. We'll come back to that in your homework. Probability, as we mentioned in the first project, and as we'll keep mentioning for the back half of this course, is a long-term average rate. So the more dice we roll, the more we're going to see that rate occur. So right now, we've got quote-unquote too many 1s and quote-unquote too few 2s. But if I keep holding down this F9 button and letting that die roll over and over and over again, we just see the rates begin to stabilize. Now, how does this relate to the real world? Well, without saying too much, you have to observe, I mentioned this before, you have to observe experiments enough times to establish these rates. Remember, we knew that these rates were going to be 1 in 6. We knew that because we're rolling a die. But in the world, in reality, you don't know what the rates are. So the only way to observe the rates is to actually look at the experiment over and over again.